A statistician's wife had twins. He was delighted. He rang the minister, who was also delighted. "Bring them to church on Sunday and we'll baptize them," said the minister. "No," replied the statistician. "Baptize one. We'll keep the other as a control." So, how do we use studies widely? We're going to consider sampling variability, statistical significance, and the use of randomization in determining what kind of conclusions we can come to from a study. So in a prior class, we looked at the Justin Timberlake data, and you can see all of these sampling distributions is what they are, where we look at the means from different samples for a class, all right? And we do see variability here. So in fact, what does this dot represent that's circled right there? Well, it is just one sample's mean average enjoyment rating of a 70. So these are averages that we're seeing here. Now, do we expect every sample to provide exactly the true mean for the population? Because remember, the true mean was like 78.4, and of course not. We expect them to be not too far from the mean, but we also don't expect it to match exactly. So we call this natural variation sampling variability, all right? And it means that different random samples are just going to have different estimates. So you can see right here, it looks like the two best methods were stratified by row and clusters of columns, probably because you had representation from the front and the back for both of these. In fact, the column clusters actually looks a little better than the stratified by row, but probably either method would work fine. Whereas you can see the other ones, we have some more variability. Now, do not confuse variability with bias, all right? I don't believe any of these are really more biased than the others. I marked the true mean very roughly on here, and all of them are sort of centered on the true mean. There doesn't seem to be a consistent underestimate or overestimate for either one of them, all right? So while there are differences in sampling variability, we don't see any strong biases in our data. All right, now there's another way to reduce sampling variability other than the sampling method, which is what we did here. So let's go ahead and we're going to look at Reese's Pieces, and there's a proportion of 40% orange here, and I'm drawing samples right now of 25 candies. So I'm going to look at averages for 100 samples, or proportions really for 100 samples. So there's our 100, and you can see the standard deviation is 0.098. Now I'm going to increase it to 50, all right? And the standard deviation is now 0.565. And it shows the previous, so you can actually see it shrinks. So see how it's shrinking a little bit compared to the light gray as I increase the sample size? And you'll also notice now our variability is down to 0.033. So you can see that it's getting tighter and tighter. It's not as obvious here because the scale keeps changing on the graph. So now you can see the variability is all the way down to 0.026. So the easiest way for me to show it to you is to actually graph the standard deviation that I got for the different sample sizes. And you can see that it definitely, the standard deviation gets better and better relative to the mean as our sample size goes up, all right? So as our sample size goes up, the standard deviation relative to the mean goes down. So it does appear, and we'll go over this later in a future unit, to be related to the square root of the sample size, just an FYI there. Okay, so what can we infer about studies, either experiments or observational studies, either one? Well, what we're looking for is when we see observed results that are too unusual to be explained by chance alone. And when we get that, we call that statistically significant. And if the probability of a result as extreme as observed is 5% or less, that's usually our guideline. It can change, but it's typically 5% probability or less. So here I have a dot plot of a simulation, all right, of the number of successes in 50 trials where n is 20 and p equals 0.4. To simulate the number of Reese's Pieces. If a sample of 20 Reese's Pieces contained less than 4 orange Reese's Pieces, would we question that the true proportion of orange Reese's Pieces is 0.04? Well, here's, on my simulation, I only got one sample that was less than 4 out of 50. So that would be 2%. So we would say that if we actually had that result for our experiment, that it was statistically significant. Now we could also, because we know binomial distributions, calculate the probability of getting less than 4 orange Reese's Pieces, and you should see that that would also be less than 5%. All right, so randomization is what allows us to make inferences since it minimizes our biases in our research. And what we can infer depends on what we randomize, because there are 2 things we can randomize. So I truly do believe that automated grading can help you because it gives you immediate feedback and it increases your engagement. You know right away if you have an issue. All right, that's my belief. All right, now let's assume I see a higher performance on district assessments for students who are auto-graded compared to those who are not. And I get those from different studies. So depending on how the study is designed, affects what I can conclude. So I did actually do this. I compared my pre-AP geometry classes in the fall before and after using automated grading. So I actually had them hand graded in the fall, automated grading in the spring. Did I do a random sample? No. Did I do random assignment? No, I just said, hey, if I'm going to do it for one class, I'm going to do it for everybody, just for teacher sanity purposes. So what kind of conclusions can I come to? Well, for geometry students in my class, there was an association. I actually really did see an improvement on district scores compared to the rest of the district, all right? So I did see an association, but I couldn't infer causation. Also, I couldn't infer to other geometry students. I could only infer about the students in my class. Now, if I could, what would have been cool would be maybe there were other teachers using automated grading. At the time, there really weren't very many. But let's pretend now there are. There are a lot of teachers using automated grading because of our virtual situation. And I could randomly sample teachers who are auto grading. And then there's some teachers who are like hand grading on Kami. So if I took a sample of classes in the district and I just recorded what method the teachers were using, all right, am I doing a random sample? Sure, I'm doing a random sample. Am I doing random assignment? No. Random assignment is hard. Trying to get a teacher to change how they're going to do something, not easy. For me either. All of us were like, oh, it took us so much effort to do this already. It's a lot of work to get auto-graded, but sometimes it's necessary. So what could I conclude from this study if I did a survey of the district? Well, for geometry students in the district. Now notice, even though I didn't investigate every student in the district, I can still infer about the district in general. Why is that? Because I took a random sample from the district, all right? Then I can't do cause and effect, but I can say association between automated grading and higher district assessment scores. So the sample infers, tells me who I can infer about, and assignment tells me if I can do association or causation. All right. So now let's say geometry classes at Cedar Ridge are randomly assigned to automated grading or hand grading. So we take all the geometry classes at Cedar Ridge. All right. Is that a random sample? No, because we did all the geometry classes at Cedar Ridge. So that tells you who I can infer about. All right. Did we do random assignment? Yes, we did. So we can do cause and effect. So my conclusion is now for geometry students at Cedar Ridge, and I can do all the geometry students at Cedar Ridge because they were all involved in our little experiment. Automated grading raised district assessment scores. All right. Now, finally, the gold standard. Let's say we could do a random sample of geometry classes in the district, and somehow I can make the teachers either use hand grading or automated grading. It would never happen because it's a pain in the butt. But pretend I could do that, all right? Then I'm doing the gold standard, which is a random sample and random assignment, all right? So I could very much generalize not only about who, which would be the geometry students in the district, even though I didn't include everyone, and I can infer causation, that automated grading actually raised district assessment scores. So that's kind of the idea of what kind of conclusions you can make based on the use of randomization in a study. All right, So, quick summary. Can we infer cause and effect? So the case where we can infer cause and effect and the population is when we have when we do randomly sampled and randomly assigned. If I only do randomly assigned, I can't infer about the population, but I can still do cause and effect. If I only do randomly sampled, I can't infer cause and effect, but I can infer about the population. And if I don't do anything, I really can't infer very much at all, except for my all I can say is, oh, there's an association for this group. That's it. All right. Sometimes, though, we want to determine cause and effect, but we really don't want to set up an experiment. So why wouldn't we want to set up an experiment to determine the impact of secondhand smoke on children? Well, that means I would actually have to randomly assign parents to smoke. And first of all, that's not good for the parent, and it's definitely not good for the kids. While we don't do experiments to say, oh, smoking caused lung cancer, and I'm going to go over why we can say we're pretty sure about a cause and effect on that. We don't like to experiment in that. Also, let's say a lot of people say, okay, social distancing and the use of masks helps reduce the transmission of COVID-19. Why don't we do some experiments about it? Well, you've noticed when they do experiments, they're looking more at droplet spread. They're not saying, oh, let me go stick you in a room with a bunch of COVID people without a mask. That would not be cool, right? So it would be unethical to expose people to illnesses without protecting them. With that said, when we do the vaccine trials, I'm going to guess that they actually do have to have some form of exposure, or maybe they just follow them. But when you're doing a vaccine trial, you really do need to do the gold standard in terms of having people that are exposed and people that aren't. I don't know how they're doing that, but I'd be curious to follow that up. So how do we establish evidence for causation when we can't do an experiment? So notice I'm going to say evidence for causation. I'm not going to say we're establishing causation. We just have very strong evidence for it. All right. Well, if the association is very strong, so like lung cancer and smoking, we've seen a huge association there. When it's very consistent, all right? And larger values of the explanatory variable, in other words, if you smoke more, you're more likely to get lung cancer. And if the alleged cause precedes the effect in time. For example, if you get lung cancer and then you smoke, that's not very evident. But a lot of people smoke and then they get lung cancer. And the alleged cause is plausible. So lung cancer, the target's in your lungs. There seems to be a reasonable explanation. So there are times that we infer causation, all right? We establish evidence for it when we don't have an experiment. But if we can, the gold standard, if you really want to know cause and effect, is experiments. That said, there are basic data ethics for experiments. First of all, if we involve humans of any type, they have to be reviewed in advance by an institutional review board. Okay, now there's not some central group, but they, or universities, organizations, they all have their review boards. There must be informed consent before data is collected. There's actually a great House episode on informed consent. I think that's the name of the episode. So watch that one if you get a chance. All individual data must be kept confidential. So if I take data on you, I cannot share like what your scores were on the AP district assessment. I can only do statistical summaries for groups. So we don't share private data. And that's a quick overview on using studies wisely.